Oh, hi, I'm Obi-Wan Kenobi, and you see me in such fine quality epic chemistry educational videos such as Chapter 1 Review, What Does It Have to Do with the Test? Part 2, and From the Darkness is the Absence of Light, Part 4. Okay, here's Chapter 2B, or not 2B. We're looking at primarily energy and matter. And all these involve some kind of energy, somehow, somewhere. So we're going to look and describe energy and give 6 examples of the 6 forms of energy. You're going to know that there are 3 laws of thermodynamics. You're going to be able to define thermal energy and how is it different from temperature. You're going to understand what is entropy, endothermic and exothermic processes and reactions. Okay? So, looking at it, energy is the ability to do work. What would the world be like if we didn't have energy? What would society be like if we had no energy? In other words, we had the energy to live and reproduce, but what if we didn't have energy in our society? Something to think about. Now, there's 6 common forms of energy out there. Mechanical, you have kinetic and potential. Kinetic is the energy of motion, okay? So, like a baseball that's traveling, okay? Or the flying fist, that would be kinetic energy. Or the wagging tongue, that's kinetic energy. Then there's potential energy, energy of position. So I have this little guide here, okay? And, oh, hey, what do you know? Went right back to it, huh? Oh, gosh. So, hang on, technical difficulty. Very technical difficulty. There we go. Let's slide on down here. Let's get us back here. So with that, we have potential energy, thermal energy, energy due to heat, acoustic, okay? So that's sound energy. And we have electromagnetic energy, okay? Which, if we didn't have electromagnetic energy, a lot of our entertainers couldn't do their jobs now, could they? Oh my gosh, can you imagine some of them trying to sing without their gear? Oh dear, yeah, that's kind of a painful thought. Okay, then you have chemical energy, where it's natural gas. Okay, batteries, when they're not being used, you've got chemical energy in them. Okay. Nuclear energy, that's pretty much self-explanatory. Okay? So in looking at thermodynamics, okay, it is a total branch of chemistry and, yeah, even physics. Because what they're looking at is how is it that energy moves and how is it energy changes from one form to another. You'd say, wait, what do you mean by energy changing from one form to another? Well, if you were to go and drag out one of the most important pieces that any teenager can have today, bam! A cell phone. How does the cell phone operate? Well, my parents pay for it and it works. That's not what I'm talking about. I'm talking about the physical thing of the cell phone, okay? You have in there a battery. How does the battery make the cell phone operate? Well, battery by itself has chemical energy in it. The chemicals react, and in the reaction we get electricity. That's what powers your cell phone. So you can text about yourself to your friends all over social media and brag about how cool you are. So, first law of thermodynamics. Energy conservation. You can't create or destroy energy. It changes form. It can be converted from one form to another. Okay? That's the first law of thermo. Because if we were losing energy and we couldn't get anything out of it back at all, then the universe is going to fall apart. And that would be bad. Let's go to the second line of second law of thermo, also known as entropy. Entropy is a fun one. All natural processes tend to the highest entropy and minimum usable energy. But wait. What are you talking about? What do you mean by entropy? What is entropy? Think about disorganization. This is why I love this graphic right here, where it has the word entropy. Here it starts out as that cute little E. Okay, and then as you're working your way through, you notice how it's getting weaker and weaker. Well, what's happening? The pixels are kind of spreading out more and more, so you can actually barely make out the Y. This is high entropy on this end. Least organization, least amount of energy. Here, it's on the other end. High energy, high organization. If we look at an ice cube that is melting, here, minimum entropy, maximum order. When we talk about melting into a puddle of water where you don't have a structure, that is maximum entropy, minimal amount of order. It's like your room. You clean your room on the weekend, like Saturday morning, because mom and dad tell you to do that, and then by Friday, your room looks like, a tornado has gone through it, and then you got to start the process again of putting everything back and reorganizing everything. Yep. For those of you who can keep it perfect throughout the week, God bless you, that's a gift. All right. So, in looking at this in terms of entropy, okay, let me pull back for a moment, okay. Here's a great example of the second law of thermodynamics. What happens when gasoline is burned in a car? Right, so some of it goes to powering the engine, right? Bunch of it gets released as heat, and then you have car exhaust, right? Can we use the car exhaust? No. See, we went from high order, a lot of order, which was gasoline, the liquid, and we went to low order, minimum amount of order, like the heat being released, the exhaust coming out. We can't use that. It's low quality. All right. So then we got to also talk about how is it particles organize themselves? Because we've looked at energy. How is it that we look at particles organize themselves? Okay. So this is where we look at how we looked at particles. So the first thing we say, all matter consists of tiny particles. Everything is made up of atoms, if you will. They move and they collide randomly. Yeah. Now, diffusion is particles spreading apart. So an example is perfume in the room. That would be a good example of that. Perfume in the room is a great one. And I'll have to see if I can do a visual for the class. Okay, as I'm going to be working my way through kinetic energy. Don't worry about the formula, but remember, particles of matter are always moving. It's kinetic energy. And the joule is a unit of energy. I'm not going to worry about that as part of a review. I'm not. Okay? So if we look at the internal energy of an object, how much energy does an object truly have? It doesn't matter if it's an ant. It doesn't matter if it's your cell phone. It doesn't matter if it is your ego. Okay? All objects have energy in them. There's potential energy, stored energy, and moving energy, the kinetic energy. If we add all those up, that's going to give us our total internal energy. Now, when we look at thermal energy, we look at all the kinetic energy of the object's particles. In other words, the heat energy that the particles have. Because remember, particles are moving. Okay? So when we look at thermal energy, it's the total kinetic energy that an object has. When we look at temperature, we look at the average kinetic energy that an object's particles have. And notice I say system. It could be an object. It could be a system like the planet Earth as a system. We could look at it that way. So wait, what's the difference between thermal energy and temperature? Well, think about this. If you were to go and take one person and take all the possible ways to measure their body temperature, are you going to get the same reading? No, you're not. Well, how come? because different parts of the human body have different temperatures. It's not much of a difference, but it's there. Fingertips tend to be a little bit colder compared to where your heart is or where your brain is. Okay, there are some differences. Okay, so the temperature, we look upon that as the overall average kinetic energy of the system's particles. Okay, then we have what's called heat transfer. In heat transfer, okay, it's the transfer of thermal energy between two objects of a substance. This is an obvious one here. Cooking eggs. How much of an obvious example? We turn on the stove provides heat, the heat goes through the pan into the egg and cooks it. That is thermal transfer. Okay? So heat is how much thermal energy is transferred from one object to another. It's not the same as temperature. I've got two glasses of water. One is much bigger than the other. Okay? Here, let me make sure, let me adjust this a little bit. There we go. There we go. So here, small glass of water, large glass of water. They both have the same temperature. Do they have the same amount of heat in them? No, this one's going to have more heat in it. Why? Because there's more energy in it. There's more liquid in it. More liquid, you're going to get more energy. But their average is the same temperature as this glass of water here. Okay? Less energy. More energy. But they have the same temperature. Because heat isn't the same as the temperature. Temperature is the average. Heat is the total amount of heat, thermal energy. So then we have to look at exothermic and endothermic. Okay? Now, I've got to pay attention to my timing here. I'm going to have to do a part C on this. There's just no way I can finish all of it. So, here's exothermic and endothermic. Let's break down the words. You know what? I think I'm going to stop here. This would be a good time to do that, and then I'm going to pick up with the third video. Okay? All right. Obi-Wan Kenobi signing off.